Hey everyone, it's Miss Johnson. Today we're going to be talking about the probability of independent, and I'm actually going to throw in an example of dependent events. Now, to start talking about probability, we know that probabilities can be shown by using ratios to show how likely or unlikely an outcome might be. Ratio, remember, another word for fraction. For example, one of our common examples is flipping a coin. If I flip a penny and I want to know the probability of getting a heads, we know that the fraction is 1/2. Why is it 1/2? Because there is one option, one outcome for getting heads is flipping heads. Out of how many options I have total when I flip a coin, I get 2 options. I could get a heads or a tails. So my fraction is 1/2. Now, what is the probability of any event? It's based on that same formula. The number on top of my fraction is represented by the number of ways an event E can occur. And the denominator is denoted by the number of total possible outcomes. So for example, if I wanted to know the probability that a day of the week, S started with an S, well, how many ways could that happen? Well, Saturday and Sunday are the 2 days of the week that start with an S out of 7 possible days. So the probability of that occurring would be 2/7. Our first example is going to be to construct a probability model for the experiment. Now, when I construct a probability model, that means I'm going to determine what all my possible outcomes are and what the probability of each of those events happening is. So I have to start with, if I flip a fair coin once, I could get a heads, first toss, second toss. Or first coin, second coin, I could get a heads, tails, I could get a tails, heads, or I could get a tails, tails. Those are the 4 options that I could get by tossing 2 coins. Now, what's the probability of each of those happening? Well, the probability of heads, heads, well, there's 1 of those events happening, and there's 4 possible. Probability of heads, tails, and let's run through these really quick. 1/4, probability of tails, heads, 1/4 again, and probability of tails, tails is 1/4. Now that's going to be kind of annoying to do for anything larger, so just want you to know that the probability model of an experiment is simply what events are occurring and what's the probability of each of them happening. Now, if I toss a fair coin 4 times, I do not want to create a probability model for that because that's going to be a lot of work. But I do want to just calculate one probability. What would be the probability of getting exactly 2 heads and 2 tails? Now, in order to calculate that, I need to know what all of my possible outcomes are. So I'm going to start by listing a few. I could get all heads. Every time I flip a coin, I get a heads. Or I could flip a coin and I could get heads, 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 and the last one could be tails. And here I go. I'm just going to list a bunch of my options. Hey, tails, heads. I could get heads, heads, and the last 2 be tails. Now, I am starting to make this and I'm starting to worry, hey, I want to make sure I get all of the number of options. I don't want to miss one, and I want to make sure I don't double count any. So remember, in order to calculate how many outcomes you should have, we can do it the following way. Well, if I toss a coin once, I'm going to have 2 possible outcomes. If I flip it a second time, 2 possible outcomes. And remember, I multiply each of those tosses by how many outcomes. So 2 times 2 times 2 times 2 equals 16. So when I'm done, there should be 16 options over here. And right now I have 4 of them. So let's continue. I could also have heads, tails, heads, heads. Now I notice I still just have 1 tails. I'm doing this kind of methodically to make sure I don't miss any. Heads, tails, heads, tails, heads, tails, tails, heads, heads, tails, tails, tails. Remember, you could also make like a little T-chart and break it off like this. That's an option to make sure you get all of them. My next option is to say, hey, instead of having heads in that first spot, I could have a tails. So tails, heads, 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 and I'm going to run through all of my options. Heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, tail, tail, head, head, tails, tails, heads, tails, and I'm gonna soon be out of options. Tails, heads, tails, 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 tails. All right, I think I have them all. Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Perfect. I have every single option there. All right, so I know I have 16 possible outcomes. And what is the probability of getting 2 heads and 2 tails? No, that's not the outcome I want. That's not the outcome. Nope. Hey, that one works. Nope. Yes, that has 2 heads and 2 tails. 2 heads and 2 tails. Nope. Nope. Yes. Yes. No. Yes. No. 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 So how many options are that? Is that 1, 2, 3, 4, 5, 6? So 6 out of 16. For if I simplify that, a grand total of 3/8. All right. Now, what happens if I have 2 events? Now, and I want to know the probability of both of them happening or one or the other. So the 2 events are said to be independent. Okay, think of independent, you're not relying on anyone. So independent if the second result is not affected by the first result. Then, if they are independent, then I can multiply those 2 probabilities together and I can get the probability of both of them happening. So if I want to know the probability of A and B happening together, I multiply those together. So an example, consider a coin. I'm tossing a coin and I'm also tossing a dice that has the numbers 1 through 6 on it. And we're going to call event A getting a heads, and we're going to call event B what's the chance of rolling a 6. So probability of flipping a heads is 1/2. We know that. Probability of rolling a 6 is 1/6 because I have one option to get a 6 out of 6 different sizes of my dice. We can reasonably assume that they're independent because flipping a coin is not going to affect how I roll my dice. One is not going to change the outcome of the other. So if I want to know the probability that I get a heads and roll a 6, I can multiply my probabilities together. 1/2 times 1/6 equals 1/12. Let's run through a couple more examples. Given the spinners above, what is the probability of spinning a 3 followed by spinning a red? So I want a 3 and a red. Now, are they independent? Yes, because spinning this spinner is not going to affect how I spin this spinner. All right, given the probability of getting a 3, well, that's one option out of, there's 5. What's the probability of getting a red? Well, there's 2 red options here that I can see. So 2 out of 4. I'm going to multiply those probabilities together. That is 2 out of 20, which simplifies to 1/10. Now I can simplify the fraction 1/2 first, but I don't really need to. Now, my second example, given the spinners above, what is the probability of spinning a 1 or a 4 followed by spinning a red? Well, if I want a 1 or a 4, I'm okay with either. That's 2 out of 5. And what's the probability of getting a green? Just 1/4. And if I multiply them together, 2 times 1 is 2, and 5 times 4 is 20, and hey, I can again get 1/10. So same probability for different things. Now, an urn contains 5 white marbles, 10 green, 8 yellow, and 7 black marbles. If one marble is selected, determine the probability that it's white. 5 out of how many marbles do I get? Okay, I get out of how many marbles total? 5, 10, 8, and 7 gives me a total of 30 marbles. So one marble selected, I get 5 out of 30, which simplifies to 1/6. Now this example is not completely complete. I'm going to add one statement. I'm going to replace the marble, and I'm going to draw again. And I want to know the probability that the second is green. Well, what's the probability that I get a green marble? That's 10 out of 30. So if I was just looking at the probability of drawing a white one, I have 5 out of 30. If I was just looking at the probability of getting a green one, that's 10 out of 30. But if I was looking at the probability of drawing both of them, so 1/6 and 1/3 of both of them, assuming I replace them, I can multiply them together, and that is a total of 1/18, which if I type in my calculator is 0.056, which simplifies to 5.56%. Remember from 7th grade, I can write probabilities as fractions or as decimals, or I can even write them as a percent. Now, 2 events are deemed to be, and we'll just skip this example. 2 events are deemed to be dependent. Sorry, those were my puppies. 2 events are deemed to be dependent, and I want you to write this definition down. It's not going to be on a hard page, so write this down. 2 events are dependent if one event does affect the outcome of the next or the second. And if I want to know the probability of A and B happening, then I calculate the probability of A, and I still can multiply it by the probability of B, but my probability of B is going to change a little bit. We're going to say probability B of after A. Now, what does that mean? Well, take this example as an example. On this first part, I told you I replaced that marble. I put it back in. Well, if let's say I don't replace that marble, I take it out and I just set it to the side. So if I wanted to use this same example right here, we'll use a different color so we can differentiate what I'm writing. If I use this same example again, except for I take out the word replace, I want to know the probability of first white, then green. Okay, of first drawing a white, then drawing a green. Well, what's the probability of my first? Well, it's still 5/30ths or 1/6. And I'm still going to multiply it by my second, but I'm no longer going to use 10/30ths because I can still have 10 green marbles in my bag, but I no longer have 30 total. I took one out when I drew the first one, no matter what it was, so I now only have 29. So 5 times 10 is 50, 30 times 29. I'm testing my mathematical skills. Let's use a calculator. Now I'm trying to remember what it was. 30 times 29, 870. 50 out of 870, let's calculate that. 50 out of 870 equals 0.057. Okay. So that is the difference between independent, I replace it, one draw does not affect the other, dependent, one will affect the other. All right. A few more definitions. Now, in probability, an outcome is A and B only when they both happen. Remember when we were talking about the intersection or the Venn diagram? When we use the word and, we're talking about when two things both happen at the same time. If one happens and the other doesn't happen, we can't include it. For example, a die is rolled. What's the probability that the number is even and less than 7? Well, what's the probability that they're even? 2, 4, 6. What are the options that they're less than 4? 1, 2, 3. Well, what's the probability that it is both even and less than 4? Remember, there's only one option and it's 2. 2 is the only one that is in both lists. And what's the total number of outcomes of a dice? 6. So my probability is 1/6. The probability of an outcome in event or is when I'm okay with one happening or the other happening, hey, or both. It's okay to be in this intersection. But remember, if I say, hey, here's probability of A and here's probability of B, notice I have circled this middle section twice. So when I'm calculating a probability, I add probability A, I add probability B, but I have to subtract the probability that they are both going to happen at the same time. So for example, a die is rolled. What is the probability that the number is even or less than 4? Well, for event A, the probability that it's even, well, there's 3 outcomes out of 6, so the probability of A happening is 3/6. The probability that's less than 4, I have 1, 2, 3. Again, it's 3/6. But remember, I have that one overlapping number. I have that 2, and I can't double count that 2 twice in my probability. So I need to take out that probability. What's the probability of both happening at the same time? Remember, we calculated that on our last problem, which was 1/6. So my probability of this one would be 3/6 plus 3/6 minus 1/6, and my answer is 5/6. That is the probability of that happening. Please, please, please remember these 2 words. Whenever you see and, okay, it has to be both, and whenever you see or, okay, it is only, it can be one or the other, and you do have to subtract that middle number. Remember, and we can multiply, or has this subtraction. A few more definitions before we finish. Mutually exclusive events are events that cannot happen at the same time. Now, when I was learning about probability, I all the time would confuse mutually exclusive with independent, because like independent, one doesn't affect the other. Mutually exclusive and independent are not the same thing. Independent means they don't affect each other. Mutually exclusive means they cannot happen at the same time. Okay. But for example, when I'm rolling a die, if I just roll it once, I cannot give an even number. You can get either an even number or an odd number, but you can't get both at the same time. But independent events, if I was rolling a die, I could get an odd number and an even number, but I'm not thinking about it as the same roll. So I'm not thinking about it as the same time. Mutually exclusive means like one instance in time. All right. By definition, non-mutually exclusive events are things that can happen at the same time. For example, if I roll a die and it's odd, it can also be less than 4 at the same time. So 2 things can happen at the same time. An example of a mutually exclusive event, all right, consider a fair-sided dice, only in addition to one of the numbers 1 through 6 on each face, we have a property that even faces are red and odd faces are the color green. So when I roll a dice, two things happen. So we're not independent. We don't have two different dice that we're rolling. They're on the same dice. An event is going to happen at the same time. So we want to know if it's mutually exclusive or not. Let an event A be rolling a green and let B be rolling a 6. So what is the probability of A happening? Well, if I'm rolling a green, all of the odd numbers are green. So that's half of them. So probability of A is 1/2. Probability of B is 1/6 because I'm rolling a 6. That can only happen 1 out of 6. But obviously A and B cannot simultaneously happen. Those are mutually exclusive. So since I cannot roll 6 and green at the same time, my probability is actually 0. So in order to multiply our fractions together, in order for P and B, in order for me to be able to multiply probability of A times probability of B, they have to be mutually exclusive. They cannot happen at the same time, or it just doesn't make sense. Now, what if I change my word to or instead of and? Well, then those events are no longer mutually. Then those events, it doesn't matter if they're mutually exclusive or not, because I don't need them to both happen at the same time. So what's the probability of A or B? Well, the probability of A is 1/2, the probability of B is 1/6, and so I get E equals 2/3. Now, why am I not including this minus A and B in my equation? Well, I'm not including it because they can't happen at the same time. Technically, I'm minusing 0. So for and, mutually exclusive matters. For or, mutually exclusive affects it. It means I don't have to subtract anything, but I can still compute something. All right, so if I'm just given probabilities and no context, notice it says the probability of A is 0.25 and the probability of B is 0.45, and the probability of both of them happening together is 0.6. So here's what I'm going to do. I want to calculate what A intersect B is. So A, what's the probability of both A and B happening? Now, how can I calculate that? Well, I can go back to my formula for OR events, which is P of A or B happening is equal to the probability of A happening plus the probability of B happening, subtract the probability that they're both happening, and I can find my missing piece of information. So what does that mean for me? Well, I know what this is. This is 0.6 equals the probability of A is 0.25 plus 0.45 plus, minus the probability of them both happening at the same time. So we're going to see if they both happen at the same time. I'm going to subtract my two values that I'm adding. So minus 0.25 minus 0.45. So 0.6 minus 25 minus 4.5. So here we go. Let's clear our calculator. 0.6 minus 0.25 minus 0.45 equals negative 0.1. Remember, I'm going to have to divide it by a negative 1. And I get 0.1. Why did I divide it by a negative 0.1? Just remember, so negative 0.1 is equal to negative P, A, and B. So divide by a negative makes those both positive. So the probability of both of those happening is 0.1. Whoops, sorry. All right, finally, given that A and this is this, and B is this, and A and B are mutually exclusive, find the probability of A and B. Well, should I multiply them together? Remember, mutually exclusive is that they cannot happen at the same time. I don't even need to do any calculations. The answer to this is a big fat 0. So if I was trying to calculate probability of A or B, I would just add those two numbers together. Okay, all right. One last piece of an example is the following. We use in statistics sometimes what is called a complement. And a complement of something is used, we use E with a bar over it. Sometimes I've seen it with E with a tally mark by it. And the probability, or I should say the complement, is all of the events that are not what I'm looking for. All right. So, for example, according to the National Science Foundation in 2004, there was a 13.7% probability that a doctoral degree was awarded in the US if it was a doctorate degree that it was awarded in engineering. If in 2004 a US doctoral recipient is randomly selected, what's the probability that his or her degree was not in engineering? Well, that is the exact opposite of 13.7%. That's we're talking about everyone else other than that 13.7%. So to calculate that, I would say the probability of E complement, the probability of not having a doctorate degree in engineering, is 1 minus, now remember to put it as the decimal, 13.7 is 0.137, so 1 minus 0.137, grand total of 0.863. So as a percentage, that is as a decimal, 0.863, as a percentage, 86.3%. All right. Last two examples. So given that A and B are independent, notice they didn't say mutually exclusive, they just said independent. One outcome does not affect the other. Find the missing probability. So 11/20 and 11/20. So 11/20 times 11/20. And we would calculate that and change it to a fraction. Not the probability of not 3/5 of the probability that B is, that we're not going to get B, and the probability that we get A and B. We want to calculate the probability of A. Then what we would have to do is we would say, well, the probability of A and B happening, and I'm just going to use notation A and B happening, is 3 equals the probability of A times the probability of B. So how would I calculate what the probability of A is? Well, I can fill in what I know. 3/10 is equal to, I don't know what the probability of A is. And you might be saying to yourself, I don't know what the probability of B is either. But remember, if the probability of not getting B is 3/5, the probability of getting B, so the opposite of this complement thing, which is the same, the opposite of not getting B is getting B. So 1, okay, out of minus 3/5 is 2/5. So the probability of getting B is 2/5. So I get 2/5. And remember, I'm going to get A by the probability of A by itself. So I'm going to divide, or I'm going to multiply, by the reciprocal. So I'm going to multiply by 5/2, and that is going to give me a grand total of, what is the probability of A? The probability of A is 3/4. Finally, I know that the probability of B is 9/20ths. The probability of A and B happening at the same time is 63/20ths. And I want to figure out what the probability of getting not A is. So we'll use our rule, probability of A and B happening at the same time. 63 out of 200. Yeah, equals probability of A. I don't know what that is. I'm going to leave that alone. Probability of B, they gave me that, 9/20ths. I'm going to solve this equation. So I'm going to times both sides by 20/9. 20/9. And I'm going to get a grand total. When I simplify, I'm going to write it over here. The probability of A happening is 7/10ths. So what's the probability of A not happening? Well, it's my complement rule. The probability of something not happening is 1. Okay, remember, that's 100%. 1 stands for 100% of all of the different possible outcomes. So 1 minus 7/10ths is a grand total of, and I'm going to write the other notation. So P not A is equal to 3/10ths. If you have any questions about any of the concepts, please don't hesitate to reach out. Hope you guys are doing great. Bye.